guys, it's time for us to move to the second problem, which is find the most stable product in the following reaction. So this is an alkyne attached with a phenyl group.
And you have a solvent D2O here, and you are given one equivalent of HOCl, which is your reagent.
Okay.
Now let's move into the question.
So what are the different possibilities of reaction here?
Yeah.
What possible products do you get here?
Yeah, I'll tell you that. First, the reagent given to us is HOCl. HOCl. If you remember from your inorganic chemistry, it will dissociate to give OH minus Cl plus.
Correct.
Now, look at the substrate given to us, which is a phenyl group and an C triple bond C.
Right.
Yeah. Now, you have an electrophile here, and you know that this C triple bond C can undergo electrophilic addition reaction.
Okay, and why this bond in particular? Why not the phenyl bonds?
I'll tell you the reason for that. Because here we have 6 pi electrons in benzene. So this ring satisfies aromatic condition.
Right.
Which is 4n plus 2 pi electrons. Here n is equal to 1. Because of this, it's very much stable. Now, if Cl plus attacks on this, it lowers its aromaticity. I'll show you how. Say it attack on this carbon. Now you get a positive charge here. Now you can see that the ring has just 4 pi electrons, and there isn't any complete conjugation for it. So it has lost its stability.
So
but
basically what you're saying is it's a bad idea for a phenyl compound to lose its aromaticity.
Yeah.
Yeah.
But if you have here a C triple bond which can undergo electrophilic addition reaction. So let's see how it happens. First thing is the RDS step, which is the addition of electrophile to it. C triple bond C H. Now there are two possibilities for Cl plus to attack on this C triple bond C. One is, say, possibility A on this carbon and possibility B on this carbon as shown. Now let's look into these cases individually. If it attacks on carbon A, say, then since it is a positive charge, you need to get negative charge here. That is, the bond will shift in this direction.
Right.
So what you'll get is a pH ring, C double bond C, a minus here, and it adds with Cl plus to give Cl, and you get a positive charge on this carbon, and H is here. Now let's look for case B. You will get the same thing, but the positive charge is on this carbon now. C double bond C, Cl is attacked here, and you got a positive charge here. Now also observe that in the question you are given only one equivalent of it. If you have excess of it, there is possibility for both these to occur. Since you have only one equivalent, only the major intermediate will be a feasible one. I say that this is major and this is minor. I'll tell you the reason. If you take this compound, you have a phenyl ring, and attached to it there is a carbocation. Now as you can see, this is in conjugation with this benzene ring, that is, it's getting delocalized. I'll show one of the resonance structures to you. You'll get a positive charge here and double bond C double bond Cl H. So there are more structures possible for it. You can shift this bond here and shift this bond here. So there are a lot of resonance structures possible. You'll learn more about it in benzene chapter. But in your GOC you have learned that because of this it's more stable. So this is the major one and this is the minor one. As you can see that here there is no conjugation possible for it. Now let's move to the second thing, that is nucleophile addition, which is the OH minus.
The completion of the reaction.
Yeah, you have pH C plus double bond C Cl H. Now OH minus attacks on this. You have pH C OH here, double bond C Cl and hydrogen on this carbon. Now this is the final product. That's what most people think, but this is not the final product. As you can see, the medium here,
basic medium.
yeah, basic medium, and you can see that you have got C double bond C OH. That is, this OH is in conjugation with this C double bond C, and there is possibility for tautomerization. Now if you do not remember the mechanism of it, you will end up getting this one. You will say that this bond shift here and this carbon takes this hydrogen, and you will write C double bond O CH. But this is not the case here, because the solvent given to you is D2O, not H2O. You have to be very careful with it. So you must know the mechanism of it and how it occurs. First thing is, it is basic medium. Also, one more thing I want to tell you, why is this tautomerization occurring? The bond dissociation energy for C double bond O is more than this CO because it's more stabilized, and there is approximately a 20 kilojoule difference between them, and so this is more stable and it is formed. Now I'll tell you the mechanism of it. You have basic medium, and you know that this OH hydrogen is acidic hydrogen. So in basic medium it takes hydrogen, and you will get pH C O minus double bond C Cl H. Now this negative charge is in resonance with this C double bond C. This can shift in this direction and this will shift in this direction. I'll write it here. You get pH C double bond O C minus Cl H here. Now come to the solvent given to us, which is D2O, heavy water. Now this negative charge takes up this, and you will get, I'll write it here, pH C double bond O C Cl H D, and this is your final product. For example, if the solvent is H2O, if H2O is given, then your answer would be pH C double bond O C H Cl H. So be very careful with the solvent, whether it is D2O or H2O, and also look for the possibility that if OH is in conjugation with C double bond C, that is like this one, there is possibility for tautomerization, and keto form, which is C double bond O, is more stable than enol form, enol, which is en, that is C double bond C, ol, COH. I think you have learned more about it in your GOC. Be careful with it. Now let's move on to the next question.
Let's move on to question number 3, in which 2,3 dibromobutane is treated with alcoholic KOH in first pathway, and in the second pathway it's treated with NaNH2 or fuming KOH.
So let's know the reagents first, which is alcoholic KOH in the first pathway, and in the second pathway we have NaNH2 or fuming KOH.
Note that though both are bases and nucleophile.
Yes. Also, one more thing you need to note is that NaNH2 is very much stronger base than alcoholic KOH. The same is the case with fuming KOH too. It's in hot condition. And now for the first part, where you have CH3, CBr, CBr, CH3 hydrogens on these carbons. It is 2,3 dibromobutane. You have treated this with alcoholic KOH. Now, if you think the product as C triple bond C CH3, then you are wrong.
Why, Gopi? Can you explain?
Yeah, I'll explain it now. I'll come back to it in a short while. And the answer is C double bond C Br CH3. Now for the second pathway, if you take, you will get as expected alkyne. Now let's look into the reason for it.
Yes.
As I've already told you that alcoholic KOH is less basic than NaNH2. Now if you take the first part of it, that is this getting converted to alkene, you have by E2 elimination, because alcoholic KOH favors E2 elimination, right? CH3 C double bond C Br CH3, this is what you have. And if you observe, bromine has lone pair of electrons, and there is possibility that, though little, but it has possibility to be in resonance, because it's a very large size, so very little is possible. And this shifts in this direction and this in this direction. You get minus charge here.
Okay.
And CH3 here. That is, this CBr bond is very strong because you are getting a double bond here,
Yes.
and a single bond here. So there is partial single and double bond.
Okay.
Yeah, as shown in this figure. Now, to break this bond, you need very strong bases like NaNH2 or fuming KOH, as shown here. NaNH2 or fuming KOH, because they will abstract hydrogen from here and favors this reaction. So for the second pathway you got an alkyne, whereas for the first pathway you got an alkene.
Okay.
So here we end up this with third question. Now let's move on to fourth question.
So question number 4. Find the products in the following reactions and also mention their stereochemistry if it's present. The first compound that we are going to be dealing with is 2-pentyne.
Yes.
Alright, and we have two reactions happening for it. We have poison sulfur and BSO4 in quinoline, and on the other side we have a reaction with nickel or palladium or platinum as a catalyst with hydrogen.
Yes.
Right? So let's get started on this question.
Yep. Yeah. First let's do the first part of it. Now let's try to attempt using nickel, palladium or platinum. All these are heavy metals, and
Okay.
if we assume this to be a nickel or palladium or platinum metal plate, now these hydrogens get adsorbed onto it.
They get adsorbed onto the
Adsorbed.
surface, right?
Adsorption.
Yeah.
This adsorption. These are good hydrogenating agents.
Okay.
That is, they add H2. They convert alkenes to
Alkenes And alkenes to alkanes?
and then alkenes to alkanes, because these are very good hydrogenating agents.
Okay. So we can just attach hydrogen and hydrogen to where the triple bond is?
Yes. Now, first consider the molecule given to us. It's 2-pentyne. It will be this one.
Okay.
And syn addition is occurring here. That is, both the hydrogens are attacking the C triple bond C from the same direction.
Same direction.
Yes. This one and this one. And you will get a cis alkene. Because as you can see, these two hydrogens have attacked from the same direction.
Same side.
This moves in this direction and this also moves in this direction. So you get CH3 and ethyl group here. So the stereochemistry of it is, it has geometrical isomerism, and the one you got here is cis product.
Okay. Now let's try it out for BaSO4.
It's not over here.
Oh, it isn't?
Yeah. It still gets converted to alkane, as I told you.
Oh, because there's hydrogen that's still present here.
Yes.
Okay.
Now hydrogen gets attacked here, and you will get CC, H here, H here. These hydrogens are already present here, and you have ethyl and you have methyl. Also note that these carbons are not chiral.
Yeah, because they have 2 hydrogen atoms each, right?
Yes.
So this basically becomes a pentane.
Yeah, pentane. So there is no point in talking stereochemistry for it.
Okay, so we just get a pentane as the end result.
Yeah. Now
Okay.
let's look for the second reaction, that is poison sulfur or barium sulfate in presence of quinoline. Yeah. I'll draw out the structure of quinoline for you, because they may ask sometimes this structure. You have nitrogen here, and if you observe this, you have poison here, which is that it indicates that the adsorption capacity of it is decreased.
Okay.
So what happens is, this converts alkynes to alkenes, but it won't convert them alkenes to alkanes.
Okay.
So the same syn addition happens here.
It'll be a syn addition itself?
Yeah.
Or can it be
Syn
from
addition,
opposite
because
sides as
it is
well?
adsorption basically.
Okay.
So you
The
have
first step remains the same.
yeah, methyl group here, and you have ethyl group. So you'll get cis alkene. Yeah, this would be the final product, cis.
Okay, so let's move on to the second reaction that we've got to solve. Let's now try and solve it for the second compound presented in front of us.
Yeah. For the second one, the reagent given to us is palladium in presence of barium sulfate. Now, this converts alkyne to cis alkane, but it won't convert this to alkene. Sorry, this is alkene and this is, it won't convert to alkane. And if you see the first part, you have C carbon, C triple bond C, single bond, a double bond here, and trans to it you have C, C double bond O, Cl. Now, if you add palladium in presence of barium sulfate plus H2, you will get a cis product, that is C, C double bond C, C, and you have trans here. C double bond O, Cl. Now this is trans, this is cis, and this is trans, because it's already trans here and it won't change now. Now if you just stop here, the answer would be wrong. This is because palladium in presence of barium sulfate has another function. It converts C double bond O Cl to C double bond OH.
Oh,
This is a very famous reaction which is called as Rosenmund's reduction. Rosenmund's reduction. You will be introduced to it in your carbonyl compound chapter. And so the final product would be C double bond C, cis here, and here you're gonna have a trans product, C and C double bond O H. So you can see now, here you have cis and here trans. Be
Okay.
careful with it.
exactly, guys. You should remember that, again, as we keep saying across all the questions, that if it appears to be too simple, there's got to be something wrong with it. So be very careful when you're attempting such questions and look at all the atoms associated with a particular compound and ensure that you've reacted all of them, right?
Yes.
Okay, let's move on to part C of the question now. Now that we've solved these two very tricky questions, let's try out the last question.
Now, the third question is very simple one, because the reagent given is sodium ethanol or sodium in liquid ammonia. You know that sodium in liquid ammonia is used for controlled hydrogenation of alkynes, and the name for it is Birch reduction. And you also were told that Birch reduction gives a trans alkane, that is C2H5 H CH3 H. Now it's very simple to write the product, but if someone asks you what is the intermediate in the reaction, what will you say? It's neither a carbocation nor a carbanion, it's not a free radical. It is both carbanion and radical. We call it as anion radical. The mechanism is a quite complicated one, but let's try to attempt this. Let's consider an alkyne, say RC triple bond C R dash, and you have metal which is sodium, which gives Na plus electrons. Now, first thing that happens is it will undergo homolytic cleavage to give RC double bond C, a radical here and an R dash here. Now we have electrons in the mixture which are provided by sodium, and these are stabilized by ammonia which you have there. Solvated electrons we call it as, and the solution appears to be blue color. We call it as solvated electrons.
Okay.
Now this gives its electrons to this radical, and what you're gonna have is R, let's draw it, R dash, either this one or C double bond C, a trans one, R dash here, negative charge here, and this one here. But just see, this is gonna suffer severe repulsions because 3 electrons are present here, they're gonna repel each other, so this is not formed. And they have less repulsion because they are trans to each other, and so this is formed. This is what we call as anion radical, as I have told you before. This is the anion part and this is the radical part. And now comes the addition of hydrogen.
Okay.
C double bond C, negative charge, R dash here, radical here. You have hydrogen in the mixture. This carbanion takes hydrogen and you will get RC double bond H here, R dash here, and a radical here. Now this takes electrons from the solution, and again you're gonna get RC double bond C hydrogen R dash and a negative charge here. And finally this also accepts hydrogen, and you'll end up getting a trans product like the one shown here, RC double bond C R dash H H. Now in the question, R is CH3 and R dash is ethyl, and the answer would be this one, as I have told you first.
Okay.
Yeah.
So now that we're done with this question, let's move on to the next question.